All right, section 4.14.3, we're going to be talking about the Pythagorean theorem and a couple other pieces of information in here as well. But this is where we're going to start, as the Pythagorean theorem. Literally hundreds of proofs for this theorem, but the Pythagorean theorem says that if we have the hypotenuse, the longest side of the right triangle C, that squared is equal to the sum of the other two side lengths, A and B, each individually squared. So A squared plus B squared equals C squared. And these images you see on the screen are just a few of the different proofs, sort of proofs by picture that you can take a look at for showing why this actually works. So what we're going to do first is we're going to use an example of a right triangle to find some missing sides. Now, the first thing I'd like you to consider is the outside triangle here, which is obviously a right triangle because you can see the pink right angle up here at the top, right? So this, in looking at this, you have to be careful. The side opposite that would be C squared. So the two sides that are not opposite that would be our 4 and our 4 radical 3. So we have A squared plus B squared equals C squared. And in this triangle, the C is the x along the bottom. So that's what's x squared. Our two sides are 4 square root of 3 squared and 4 squared. All right, so because this is multiplication, we have a property of exponents that says I can apply the squared to each of the individual pieces inside. This makes this 16 times square root of 3 times 3, square root of 3, which is 3, plus 16 equals x squared. 16 times 3 is 48, plus the 16 that's already there is 64. And so we find out that our x squared is equal to 64, meaning our x is 8. And there aren't any units on this one, so we just have 8 for x. Now coming back over here to this diagram, you have to realize that down here now is 8, but you're supposed to be finding this height, y. There's a couple of things you could do. One of the things you could do is you could recognize that we could find the area of this shape. That might not be a bad idea. But I like the idea of doing this with similar triangles instead. So we have a right triangle in both cases, and we have angles that pair up nicely. So we're going to look at right triangle similarities here in just a second. All right, so one triangle that you could look at is you could look at the left-hand triangle right here and the right-hand triangle right here, and those are actually similar triangles. The problem with both of those triangles is that you don't know the denominator piece, not the denominator, excuse me, the base piece in either one of them. They add up to 8, but you don't know individually either one of them. So I think probably what the easier thing to do is to take a look at the outside one overall. So let me redraw that one down here. So I have 8 here, 4 square root of 3 here, and 4 here. And then we can look at either one, the left hand or the right hand triangle, to find the value for y. I'm kind of liking the right triangle because I have 4 instead of 4 radical 3. So I'm going to use this one. Okay, so the right angle itself is right here, and then the 4 is opposite that right angle, correct? So we have, well, I'll redraw it. Let me move these over here just a second. We have this triangle over here. Down here at the bottom is my right angle. This is the 4. The part that I'm most concerned with is identifying the side 4 and the height or the base with the correct values. So clearly this one's opposite the 90 degrees and so is this one. So these are the two that are in proportion to one another. But y is the one that I'm looking for, in particular right here. So the question is, which one does this value y pair up with? And what you can think about up here is that if you have the angle, let me change colors here. If you have this angle, let's say right here, theta, then this angle right here would be 90 minus theta. Oops, not Q, theta. Because we have 90 degrees left over in the right triangle after the bottom angle, which is the right angle down here, is already taken care of. So this piece at the top would have to be 90 minus theta. But the whole piece is 90, which means this piece also must be theta. So this measurement at the top, theta, matches this measurement over here at the right, I'm sorry, at the left, theta. So as we're taking a look at this, this y is actually occurring along the side that is the longest right? It's actually occurring along this 4 radical 3 in our triangle, so the thetas are matching up. And then over here, you have 90 minus theta, and this one would be the 90 minus theta. So I have the ratios corresponding as 4 radical 3 in the bigger triangle to y equals 8 compared to the 4 in the smaller triangle, and we can cross multiply this. So we have 8y equals 16 radical 3. And then in solving for y, we just need to divide by 8. So the y is going to equal to 2 radical 3 in this diagram. Right, it's also true that the triangle with sides of lengths a, b, and c, a squared plus b squared equals c squared, then ABC is a right triangle with the right angle opposite c. So basically it's the same. We could say it in the other way around. We can start with a right triangle, the Pythagorean theorem holds, or we can say if the Pythagorean theorem holds, then we for sure have a right triangle. So if we're wanting to decide if 3 numbers can represent the sides of a right triangle, we can test them. These are the 3 possible numbers. The 2 smaller ones would have to be a and b. We do not have a choice with that. So it would be 10 squared plus 16 squared. And the question is, does this equal excuse me, 24 squared? So clearly 10 squared is 100. 16 squared is 256. And then 24 squared is 576. So I'm pretty sure we can see pretty quickly that this is not going to be equal. We have 356 on the left, we have 576 on the right, not equal values. We have some special right triangles, 2 of them in fact. One's called a 45-45-90 right triangle. It has an isosceles right triangle as well. So if you take a look at your diagram, it's basically, looking at it this way, you can be thought of as half of a square. In general, it's a right triangle with legs of a. It has a hypotenuse of a square root 2. So in other words, if you knew for sure, and you do know in this one that these 2 sides are the same, then you would have a squared plus a squared equals c squared, right? So 2a squared equals c squared, or a squared equals 1/2 c squared. We'll just keep right on going. We're a square root. So a, the sides of the triangle, equals c. And then the square root of 1/2 would be the square root of 1 over the square root of 2, which can be rationalized as square root 2 over 2. So this ends up being a square root 2 over 4, over 2, c. Oh, I'm sorry, they've got it set up a little bit differently than I was headed to. Let me just backtrack a little bit. Let's go back over here. I'm not going to move the 2. They solved it for c. I apologize. Alright, sorry, let's go back here. They've square rooted right here. There we go. You've got the square root of 2 times a equals the c right here. So the isosceles triangle, if the length of the hypotenuse right here is c, then the length of each of the sides is c, is the same value, radical 2. A 30-60-90 triangle also has special values. It's half of an equilateral triangle, so if you had a 60-60-60 equilateral triangle, and you split it in half, you would actually have this other special right triangle. And in general, the 30-60-90 triangle, the length of the hypotenuse is twice the length of the shorter leg, which is the side that's opposite the 30-degree angle. And the leg opposite the 60-degree angle is square root of 3 times the length of the shorter leg. So you have some measurements here where you can see this happening, right? So here's the length of 1 right here. Sorry, let me try that again. The length of 1 right here. This length is double it right here. And then what this is saying is that over here, this would be square root of 3 times that length 1 at the bottom for the height. That is this measurement from A down to the segment BC. All right, so what we're going to do is we're going to compile some of this information together with our area formulas to try and figure out how we would find the area of, say, an equilateral triangle. So we know that the area formula is we should have 1/2 the base times the height. Now, of course, in this diagram, the base is the side length S, but we do not know the height. Or do we? Well, we actually do. We can use that last information on the last screen to talk about the height of this triangle. So let me put this, in fact, I don't even think I need to draw it again. Let me just draw it inside of here. These are equilateral, so this measurement of all the angles is 60 degrees. And then when it's split into these two triangles, to this height of this triangle to show up, we have a 30, 60, 90 triangle. So if this is length S over 2 now, and this one's length S, then the side opposite the 60-degree angle should be the smaller length, that would be the S over 2, times radical 3. So S square root 3 over 2. That is the length. And S is a terrible letter to use because it starts to look a little bit like 5s. But just keep in mind this is an S in this particular problem. So my height here is actually S square root 3 over 2. And then we can simplify this to actually combine the values that are the same. So this is S squared, square root of 3 over 4. All right, another thing that we're going to take a look at in this section is the distance formula. The distance formula tells us how to find how far 2 points are away from each other by using the shortest distance between them. And the way the distance formula works is that we take the difference in the x values and we square it. Take the difference in the y values and we square it. We add those two values together and we square root the sum of that of those two values. So we're going to do an example right away. We have the values from 2,5 to 6,8. So we're going to find the distance between these. So this is the square root. We have the difference in the x values. So 6 and 8. The difference between 6 and 8. You probably count this up as 4. If you can't, and you want to write down 2 minus 6 or 6 minus 2, either way, you're going to get 4. 4 squared. We have the 5. 6 and 2, is 4. And then we have the 5 and the 8. There we go. And the difference, or the distance between 5 and 8 themselves is 3, of course. So this is plus 3 squared. And then we simplify. This is 16 plus 9. 16 plus 9 is 25, so this is the square root of 25. And the square root of 25 is 5. So the distance between these 2 points is actually 5. All right, this one says to find the perimeter of a triangle with vertices 0, 0, negative 4, 3, and negative 5, 0. A picture would be great if you want to use a picture. That would be just fine on this one. Basically what you're needing, though, is you're needing to know the distance between all 3 of these points taken 2 at a time. So we need to know the distance AB. We need to know the distance BC. We need to know the distance AC. So we're going to find each of these 3 distances and we're going to add them up. Okay, so we're going to do these one at a time. Of course, it's very nice to work with the point A because it's 0, 0. But we're going to find AB first. So the distance from A to B will be the square root. And of course, the distance from 0 to negative 4 is 4. So this is 4 squared. The distance from negative 3 to 0 is again 3, so that's 3 squared. We already did this one actually, didn't we? So 4 squared is 16, 3 squared is 9, this is the square root of 25, or 5. This one's 5, so that's AB. We're going to keep going in order. BC is next. Alright, so from B to C we have to be a little bit more careful. B to C doesn't have as many zeros in it, right? So here we are and here we are. Alright, so the distance between negative 4 and negative 5 is actually just 1, so that's 1 squared. The distance between negative 3 and 0 would be 3 squared, so that one's 3. So this is the square root of 1 plus 9, which is the square root of 10, and we can't simplify that one, so that one will just have to be as is. So we've done AB, BC, now we need to do AC. Again, AC is quite nice because A has a lot of zeros in it, and actually C has a 0 in it as well. So the distance between -5 and 0, of course, is 5. So that's 5 squared. The distance between 0 and 0 is 0, so that's 0 squared, right? So with the square root of 25, square root, we find 5. And then we're going to add these three together. So we have 5 plus the square root of 10 plus 5 would be 10 plus square root of 10. That would be the perimeter of this particular triangle. Our equation of a circle is awfully similar to the distance formula. The first center, the circle we're going to talk about is the center with the circle with the center at the origin. We're always going to let the radius be r, and point xy is a point on the circle anywhere we'd like. So in general, the equation of a circle with a center at the origin and the radius of r is that x squared plus y squared equals r squared. And if that doesn't look to you like the Pythagorean theorem, you might need to take a look at that again, right? X squared plus y squared equals r squared. Now, when we generalize this to the center at hk, so the center is no longer specifically at the point 0, 0, we have x minus h squared plus y minus k squared equals r squared. So you can see the similarity back to the last formula, hence it must be similar to the Pythagorean theorem. But also notice if you took the square root of this, you'd have something that looks an awful lot like the distance formula. X minus something, right, x minus h squared plus y minus something, y minus k squared, and then it would be square rooted. So this also goes back to the distance formula. So we're going to do a couple of examples. This one says to find the equation of a circle at the center -3, 2, radius square root of 5. So we're going to use that basic formula that I just wrote down on the last slide. X minus h squared plus y minus k squared equals r squared. Its center is -3, 2. So when I do x minus -3, I get x plus 3 squared plus, and then I do y minus 2 squared. And then I need to have the square root of 5 squared, which of course will be 5. So I end up with a formula, or an equation for my circle of x plus 3 squared plus y minus 2 squared equals 5. And that's the equation for this circle. And then we're going to go the other direction. We're going to take an equation of a circle and we're going to find the center and the radius. So the center, of course, of this circle has to be identified by what's grouped with y and x. Now, it looks a little bit funny because y doesn't seem to have anything grouped with it, but it does. The other thing that looks funny is that this has a plus sign, but of course the formula itself had a negative in it, right? So what do? Well, in very much the same way that this one ended up being x plus 3 because we did minus a negative, that means that the center is also a negative. So the center would be -3. The number here grouped would be 0. Okay, so this is my center. -3, 0, because x minus -3 would be x plus 3. And then the radius, be careful again, this is r squared. So what number squared gives you 16? 4. So the radius is actually 4.